And you can't, at some point, there are things that become counterintuitive. If you trust your instinct, it's not going to work. All right, we're done with mean value theorem. The weird thing about that problem is why did I come up with that h of x, right? That h function, like where did I come up with that, right? Why did I think to do that? And that's not my thought, that's someone else's thought. In other words, someone else proved that and I'm showing you that proof. That's what makes math hard. If you study pure math, is coming up with those things on your own. Those are hard things to do. But you get better and better at it and it takes time. All right, the last topic that will be on the test is the almighty Newton's method. Newton's method. Now, Newton's the father of calculus, right? Along with Leibniz. Newton realized that we need to try and find an efficient way to solve equations. And he realized that he could use the derivative to help solve equations. So I'm going to start this problem by showing you a picture, or this whole thing with a picture. And keep in mind with this, as we go through this method, Newton's method is an algorithm. You all know what an algorithm is? It's just a process, a set of steps. Yes, it's just a process. And we use this algorithm in a computer program to solve equations. So when you type into your calculator, you know, solve a quadratic, because a lot of these graphing calculators have a solve feature, most of your calculators are running some variation of Newton's method to get the solution. And I'm going to show you the algorithm. We're going to use the algorithm by hand. We're going to go, crap, that's kind of tedious. It'd be better if we had a calculator, and we're just going to appreciate the fact that that's what our computers are doing. But we need to see where it comes from, because the computer's not smarter than us, right? The computer can only do zeros and ones. It's the program that we write that makes them smart, and Newton was able to come up with an algorithm to put into the computer. So here's the idea. Let's say that you have a function, f. I'm going to draw it in red. Just like we had that cubic function a second ago. This is some function f of x. And I would like to know where it crosses the x-axis. That x-intercept would correspond to setting this equal to 0, and that could be any equation, right? Any equation you want. Newton said, look, what if I just pick a guess to the answer? Let me guess what the answer is. So just come in here and kind of blindly pick a number, boom, right here. Let's just pick this number. And let's call that x sub 0. That's my first pick as to whether or not the equation, that's my first pick for the answer. I can show you an example. If I did x squared minus 2 equals 0, all right? And I ask you, what's the solution to that? Everyone would say plus or minus root 2, right? Now, instead, look at the left side as a function and graph it. It would look like this, right? And we know that the true solution is root 2 over here, and then over there negative root 2. I could pick an answer like 3, and that would be wrong, wouldn't it? That's what I'm doing over here. I'm picking an answer that I know is not going to be correct. And you may be saying, well, what the heck are you going to do with that? Well, here's what I'm doing. I'm going to go up here to the function, and it's going to have a y value at that point, right? So I can plug that value into the function and get a y value. Now, does everyone agree that at that point I have a tangent line? Okay, I'm going to draw that tangent line here as best I can. And I'm going to extend that line all the way through down through the x and why is this not drawing? Okay, there we go. All right. See that? That's my tangent line. Do you see where it hit the x-axis? Isn't that closer to the real answer? I'm going to call this x sub 1. And I'm going to repeat the process. I'm going to go up again. From there, I'm going to draw a tangent line again. And do you see what's happening? This next point where that tangent line crosses is even closer. And then I repeat the process again. Tangent line again, it's even closer. Repeat the process. And you can do this over and over and over and over. And what's happening is that this guess that you made, like over here, my guess would have been 3, right? I run this algorithm one time. So I go up, I come down with the tangent line, I see where I cross, right? And then I look at that number, I say, okay, well, how big is that? Or what's that number, right? And then I go up and do it again. And what I'm going to have is a sequence of numbers that's marching towards something, right? How do I know when I'm there? Because, I mean, I'm never really going to get there, am I? I'm going to keep on getting closer and closer, but I'm never really going to get there. So let's imagine if I were to start writing out this sequence of numbers, if I were. What is square root of 2? Like, what's the real answer? It's approximately 1.414, something like that. So what would happen here is the first time I ran the algorithm, I would start at 3. The next number I would get would be like maybe, I don't know, I'd have to run the algorithm, but the next number I get might be like 1.835, let's just say. Then let's say I run the algorithm again and I get 1.576, okay? And I run the algorithm again. This time I get 1.446. Then I run the algorithm again. I get 1.419. And then I run it again. I get 1.414 something. And then I run it again, 1.414 and then something. In other words, at some point, you start getting close to the answer. Like 1.414 is pretty close. And the more you run the algorithm, this stops changing as much. It's the stuff further down in the decimal that's changing. But you start to narrow this thing into like within a range that you're happy with. I mean, we know that even in the real world, we can only manufacture things to a certain precision. So this Newton's method doesn't give us an exact answer, because the exact answer is root 2, which is an irrational number. This decimal goes on forever and never repeats. But we can get the answer as close to the true answer as we want. And that's good enough. That's what a computer is going to spit out. So when you right now on your calculator type in square root of 2, right? When you do that, it is actually doing this. It's running the algorithm on that equation. See, what it does is it says, you type in root 2, right? It says, I want to know what that is, right? Now, again, this is an algorithm that it's running. So it does this. It's doing something like squaring both sides. And then it's realizing that that's going to be an equation. If I move the 2 back over. And then it's calling that the function. And then it's operating a Newton's method on that function. It's running the algorithm until these numbers stop changing to some predetermined tolerance within the program. It says, look, if you start doing this, once the 8th digit stops changing, stop and spit that answer out and put it on the screen. And you get what? 1.41421356. All right, so yours, that's where it stopped. Now, if you go into the settings on your calculator, you can have it go out more digits. And what that would do is it would change the algorithm to run the routine more times until that digit you say stops changing. Does that make sense?
And it does it all instantly.
And that's what makes the algorithm so beautiful, is that if we do it by hand, we'll be here for half an hour. But the computer does it like that, right? That's the advantage of the computer. It can do arithmetic much faster than we can. And it's not going to make mistakes.
So back in the day, that was right.
That's right. Back in the day before computers, you could use Newton's method to get numerical solutions to any equation, pretty much. You needed this. Look, Newton's method can fall apart. Okay, it's not perfect. There are certain functions where it can have trouble. One would be something that has like maybe a sine or cosine in it that has a lot of waves going around, because then you can try and find this number, and then you pick a tangent, like let's say here, and it throws you over here. then that tangent throws you over here, then that one throws you back over here, and you can start getting thrown all over the place. If the function is weird enough, Newton's method won't converge. But that's why I said that your calculators and computers have some form of Newton's method. There are modifications that have been made to this method where it's more effective to more functions. All right, but this is kind of like the, the foundation of the ideas from this. And there's actually another method. There's a method that's even more primitive than this, which is called the bisection method, which just looks for, your calculator just goes in there and picks a point here and here. It looks for a sign change. If it changes from negative to positive, it knows that the answer is in there. So it cuts that in half and then looks on each half and looks for the sign change. Like, where did the sign change happen? And then it picks whatever half it happened on and then halves that. And then looks at which half of that did it happen on. Does that make sense? That's called bisection method. It works. The problem with the bisection method is it has a higher operation count. It takes a longer time for that method to actually narrow into your number. Newton's method is what we call converges faster. It's more efficient. It uses less resources from the calculator, less operation counts.
Yeah, because sometimes, I mean, those T80, whatever, they'll like take a while.
Mm-hmm. Yeah. Yeah. All right, you understand the method? Now I'm going to give you the option. Do you want me to just give you the algorithm, or do you want me to actually show you how to create the algorithm from the picture?
Which one's more valuable?
What do you want?
How to create it.
Say it. You just want it? You just want it? You want to see where it comes from? All right. That's what I was hoping you would say. That's what I was hoping for. I always like it when people want to know where things come from. That's good. All right, let's see if you can keep up with this. All right, so here's what Newton did. Remember, I'm going to try and come up with a sequence of points, right? That try and go to here. So he said, first of all, let's pick a number x sub 0. So x sub 0 is our first guess. And your calculator actually will do that. It'll make a first guess as to the solution. I don't know if you've ever seen on your calculator that when you solve an equation, or like if you're really good with your calculator, you know that if you graph an equation, you can find the x-intercepts by using the intercept function on the graph. And it always asks for a lower bound and an upper bound. That is helping the calculator with that first guess for the method. It's giving it a window to look in, because if you don't give it a window to look in, it's going to try and make its first guess outside that, and then it could take off. The method could fall apart. So, you know, those of you, if you use the bounds, that's what it is. All right, so first guess is that first number. Now, when we plug this in, we will have up here a point, and that point will be x sub 0, f of x sub 0, right? Whatever the function is, you plug the x sub 0 in. Then we look at the tangent line comes down here, and it hits right here, right? I want to know the x-intercept of that line. Do you agree?
Yes.
First, can you give me the equation of that line? What's the equation of this line right here? What's the equation of it? Y minus y1 equals m times x minus x1. That's what we'd use? Okay, so I'd write down y minus, what's y1? So these are 2 points, right? This is 1 point, or I'm using, sorry, shut up, Robert. Okay, y minus y1, this is y1, right? Okay, f of x naught equals m. What's the slope of that line? It's the tangent line.
Oh, so
that's the derivative of the function at that point x naught, right? Isn't that m? The slope of this line is the derivative of that red function at that point. That's m. And then x minus x naught, right? Does everyone agree that this is the equation of this tangent line? But I want to know what that point is. And this point right here is on the x-axis, right? which means the y is 0, isn't it? So let's take this equation right here, and let's replace y with 0 and solve for x. Not x naught, because x naught was already given, right? So let's replace this with 0. We get 0 minus f of x naught equals f prime of x naught times x minus x naught, right? So that 0 is not even there? Okay. What now? Let me do this. I'm going to divide this out because I'm trying to solve for x, right? I'm going to just divide this on both sides. Can I do that? All right. So I get, the 0's gone, so I get negative f of x naught divided by f prime of x naught equals x minus x naught. I almost have x naught or x by itself. I just need to add x naught to both sides. So if I add x naught to both sides, I get x naught, and then I have minus f of x naught over f prime of x naught equals x, yeah? And that would give me this point, wouldn't it? Oh, sorry, this point, right? Wouldn't it give me that point? And what did I want to call that point? If this was x sub 0, that should be x sub 1, right? So that x sub 1 comes from this formula right here. So I could actually take this formula right here and call that x sub 1. You with me? Then what do you think x sub 2 would be? What would the next point in here be? X sub 2 would be, you would do the whole same process again, right? But instead of starting at x naught, you would start where? x1. So x sub 2 should be x sub 1 minus f of x sub 1 over f prime of x sub 1. Then what would x3 be? X sub 2 minus f of x sub 2 over f prime. And we have a general formula. And that's the algorithm. That's what I'm going to write down now. So the formula is this. X sub n, the nth one of these, will be equal to x sub n minus 1. So whatever this number is, right? Minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. And this works when n is bigger than or equal to 1. This formula works. That's Newton's method. That's the formula. So what your calculator does, very quickly what it does is this. It takes the derivative, it takes your initial guess, and then it plugs it in here, 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 and computes. And that becomes the second number. And then it puts the second number into this, and that spits out the third number. Then the third number goes into this, and it spits out the fourth number. And it keeps doing that over and over.
What is it decided? What is it
Gotcha.
decided to stop?
Let's actually do a problem. Okay, I've got 20 minutes. I think we can do an example. That should be enough. So I'm going to do x to the 5th minus x minus 1 equals 0. X to the 5th minus x minus 1 equals 0. And what I want to do is approximate the solution correct to 4 decimal places. X to the 5th minus x minus 1. Nobody in here is going to be able to give me that solution with any algebraic method they have. It's not happening. So like even in a college algebra class, as good as our methods are, we don't have any algebraic methods of solving this. All right? Not going to happen. So we start by defining the left side of this to be f. And then we're going to need its derivative, aren't we? 5x to the fourth minus 1. Now we do need a calculator to do this, okay? Newton's method is highly computational, so I'm going to use my calculator today. All right. Let's write down the algorithm, just so we have it here. X sub n equals x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. Boom. There it is, right? That's the algorithm I'm going to use. What is the first point that we're going to start with? We'll call it x sub 0, right? And that x sub 0 is a guess. So let's make an educated guess here. What number looks like it might be close to making that equal to 0? Well, what happens if we plug in 1? You get negative 1. That's close to 0. What if we plug in 2? Uh-oh. That's pretty far away from 0, isn't it? 0.5. So let's just start with 1. I mean, it's close, right? It's a nice number. Let's just start with 1 and see what happens. All right? In the problems in the book, they give you the starting point. Okay? I'm just saying, hey, let's just think about it. Like 1. 1 seems to be okay, right? All right, so let's start with 1. All right, so we have the first one. Yay. Now, to get the second number, right, x sub 1, it will be equal to, using this formula, x sub 1 will be equal to x sub 0 minus f of x sub 0 over f prime of x sub 0. Understand? The first one, right, this is the 0th one. The first one will be the one before it minus the function at the one before it divided by the derivative at the one before it. Now let's plug in that. What was x sub 0? It was 1. Minus, what's f of 1? We'll have to do that. And then what's f prime of 1? These might be easy. This first one might be pretty easy. What's f of 1? We've already did that. That was negative 1, wasn't it? When we plugged 1 in? So we get negative 1 on top. Over, now on the bottom, let's see, the derivative with 1 plugged in. What's the derivative with 1 plugged in? 4. So this is equal to 1 plus a fourth? 5 fourths? I'm going to write that as 1.25. Is that okay? And that's exactly the answer, right? 1.25. That's x sub 1. With me? What we want to do is we want to continue this process until we are correct to 4 decimal places, which means we want to do this until the first 4 decimal places stop changing. Yeah, I haven't done this problem, so I don't know how many steps it's going to take. So should we continue? Yes, of course. All right, so let's do x sub 2. X sub 2 will be, let's see if we can do it without writing the whole algorithm out. It should be x sub 1, right? Is there a question? Yes.
Did you get the negative 1/4?
Right here?
Yeah.
I think we plugged 1 into the original function, which was right here. So it was 1 to the 5th, which is 1, minus 1, which is 0, and that leaves you with negative 1. Then the bottom was 1 into this one, into the derivative, so you get the 4. All right, so for x sub 2, I'm taking this answer and plugging it into the algorithm again. So it'll be 1.25 minus f of 1.25 over the derivative at 1.25. Yeah? Calculator time. Now, since we're going to go to 4 decimal places, whatever we get on our calculator, let's go to at least 5 decimal places or 6 so we don't get too much rounding error. So what happens when you plug 1.25 in here? So 1.25 raised to the 5th minus 1. I'm getting on the top here. I'm getting 1.25 minus just the top, 0.801757. I'll be like overkill here. I'll do that. Is that all right with you? Anyone else get something close to that? All right, over. Now I need the same number, 1.25, plugged into the derivative. So raised to the fourth times 5. Oh, wait a minute. I think I did that twice. Oops. Minus 1. Anybody getting 11.207 something? Okay, so you should get 11.207031. Good enough. I'm going to take this number and divide it by this number now. So I have 1.25 minus, I'm getting 0.0715406, something like that. Anyone else? And so now I do this minus that. Which gives me 1.178459. And that's x sub 2. And then I repeat. This time, x sub 3 will be, I think this is the last one I'm going to do, all right? Because I think you get the idea. How long would it take what?
Get to 0.
You're not trying to get to 0.
I'm trying to get to a number.
Yeah, look at our guesses were this. X sub 0 we got was 1, right? X sub 1 we got was 1.25. X sub 2 we just got was 1.178459, right? What I want to do is I want to look out the first 4 decimal places. And I want to go and keep going until the first 4 decimal places stop changing. They're still changing, aren't they? The first 2 are still changing. Do you see why this is perfectly suited for a computer?
Yes.
Okay. In fact, I've had students in the past that are like pretty good with these actually write a program in this to do it. You can write the program in these to do this algorithm. You could probably, I've done it several times. I don't think it's on that one. Well, maybe I do have it in there. Who cares? Doesn't matter. You could Google it, how to program Newton's method into a TI, and it would do it. But why would you do that? You can solve the equation on the TI anyway, and it's doing that in the background, right? Yeah. All right, so let me do one more. X sub 3 will be X sub 2, which was 1.178459. Do not round that, okay? We need all these decimals. We need to keep the precision as good as possible. That's X sub 2 minus f of x sub 2, so f of 1.178459. There's a lot of room for error here, right? Doing this by hand? Which again is another reason why the computer is more efficient with this, because it doesn't make arithmetic errors. I'm sorry? Yeah. Then you have bigger problems. All right, I'm going to try this. I'm going to try and, does anyone have this one worked already? You do? Give me what you got.
0.0943.
Wait, did you do the whole thing?
No, just the echo.
Oh, you did that, okay. Yeah, that's fine, I'll take that one. Hold on. Okay, so you have what?
0.09439944.
Good, that works. Okay, and then over, we still have to do that one. Oh, you got that one already?
8.6433496663.
Okay, good enough. Have you put all these together yet, or are you still working on that?
Not with all of them.
Okay. Well, look, let's do this division here. Check out this division here.
How do you do that thing where you like copy and paste it, just move your arrow up.
Yeah, it kind of depends on what calculator you're using. I'm getting 0.0109216. Anyone getting that for that last piece? And then this first, sorry, this is in front of it. So what can you tell me? Are we going to be there with this or not? Look, we had this number, right? This was the original number, x sub 3 or x sub 2. And what are we subtracting it from? What are we subtracting from it? Something that goes out into the 10th, 100th place, right? It actually changes here. It's going to change my 100th place here, isn't it? So I'm actually not going to get to where I need to get to until this piece at the end, right here, that I'm subtracting, is like 0.0000 something.
Because like right there, you just...
Yeah, I just modified this, right?
Your first decimal place stays the same.
Yep, our first stayed the same.
So here's a good question on the test.
I'm not gonna ask you to do one of these on the test. I want you to practice, not as a problem. I mean, this would take too long.
That's what I'm saying.
Yeah.
Would you give us one that would be solved within like 3
I might offer this more as a bonus problem more than anything else, because it's really time consuming and tedious. And the point of this is not that you can do it by hand. It's for you to appreciate how wonderful the method is, because it allows us to solve equations. That's where I'd be right there. Just practice. Yeah, don't focus on this too much at all. Yeah. This would be, you've got some spare time, you're watching football and just want to do a couple of problems.
Figure out how long it's going to take for the ball to get to the end zone.
Now, I had planned on doing some problems in class, so why don't we do this? You see the class problems I have there at the bottom? My intention was to try and do those today in here, like let you work in groups doing those, just to kind of guide you. But I actually thought our test was on Monday, so I was cramming. So that's why I took my time on this today. So on Monday let's make that just a kind of review, answer question day. All right? Well, I mean, I don't want to say let's change the test to Monday. All right? And so... And I don't want to throw any more information at you, so, but that means you come in prepared. You know, do some of this stuff over the weekend. Come in with questions, and that's about it. Yeah. Have a good weekend, everyone.
What day is this from?